Hello. Am I?
Hello, sir. Hello, sir.
Yeah. Am I audible?
You are audible, sir?
Fine. So let us start. Wait a minute. You joined from two devices?
Sir, from multiple side joints, sir.
Okay. But I am seeing two little princes of my mother.
Sir, 1 minute.
Don't know why. Can you see this screen?
Yes, sir. I can see two. Yes.
Yes, there are two princes of my mother. Fine. Okay then. Let us start. Where were we in our last class?
Sir, we're discussing problems on for part.
Yes, now. So till now we have seen electrostatics from the basics. We have seen the Coulomb's law. We have seen the application of Coulomb's law, its limitations, and several examples also we have seen. Now let us come upon electrostatic equilibrium. First of all, tell me, what do you understand by equilibrium? Do you understand anything? What do you think equilibrium stands for?
So, when
Yes, Devan.
rest vacancy, no forces are acting on.
No forces are acting. Is is that a correct definition? Means like if you are pushing a wall, if you are pushing a wall is still at rest. Does it mean you are not applying force? Or
No,
does it mean wall is not in equilibrium?
sir. No, sir.
You
The
are
net.
applying the force. You are applying the force, but still the wall is not moving. Wall is in its equilibrium state.
You can say
Then what should be the
resistance.
correct definition?
The total net resultant force acting on the body is zero. You can say.
Net resultant force acting on the body should be equal to zero. So its definition would become, so a state where the resultant force on a particle is zero. Here we are dealing with electrostatics and we are going to study electrostatics equilibrium. That's why we will use charged particle, not simply a particle, but a charged particle. So it is a state where the resultant force on a charged particle is zero. And any point in the space where this net force is zero, that point will be called equilibrium position. Okay. Now there will be some types of equilibrium: stable equilibrium, unstable equilibrium, and neutral equilibrium. In stable equilibrium, what will happen? The particle will try to again come back at its previous position. Just in the case of this bowl, a ball is there. This example is given in mechanics actually, but I've taken it here just for a clear understanding of equilibrium position. So when a ball is kept in a bowl like this, a spherical bowl, hemispherical bowl it is, and if ball is pushed aside, little bit aside, like on left or on right, then what will happen? The gravity will again pull the ball downwards. Because of that, the ball will again come back to its original position. And if you push the ball on left hand side, then again it will have a force on the right hand side direction. Means anywhere in the bowl, if you are pushing the ball will again come back to its original position because the force will be directed towards the center of the bowl. Getting it? So whenever such a equilibrium is there, such an equilibrium is there that the particle does not leave its position but again comes back at its original position. That is called a stable equilibrium. What is called? A stable equilibrium. Understood this?
Yes, sir. Understood, sir.
Next is unstable equilibrium. Now in unstable equilibrium, what is the case? It is similar to the inverted bowl. an inverted ball. A small ball is kept upon this inverted hemispherical bound. This ball is not moving anywhere, means the ball is in equilibrium position. But if, in any case, you give a slight push, you give a slight push to this ball, even if you blow the air out of your mouth over this ball would start rolling downwards and it would never come back again. Why? Because gravity only pulls. There is no force which is going to pull back this ball again to the equilibrium position. So this such an unstable such an equilibrium is called unstable equilibrium, because if any force is applied, then the body is not going to restore its original position. Means restoring force is absent here. Their restoring force was not absent, it was present. Got it now?
Yes, sir. So means restoring will be present, but it will not go to the initial position. I can say that.
It will not go to the
Initial position. We can say initial position.
yeah, it will not be able to go back to its initial position because external force is not there. Okay. Now third is neutral position. Sorry, neutral equilibrium. In neutral equilibrium, what happens? Every new position is an equilibrium position. Every new position is an equilibrium position. Like the charge is there in your hand, it is an equilibrium position. And if you are moving it to any other place, there also it is equilibrium position. Then such an equilibrium is called neutral equilibrium, where the displacement is not having any effect on the particle. Okay. Now, question is find out the value of charge q for which the following system remain in a state of equilibrium. Hmm. Try solving it. Yes, this is an equilateral triangle. In this equilateral triangle, all these angles are 60 degrees. Okay. How can we say that it is an equilateral triangle? Because all the sides have equal length, and A. Solve it now. Try solve. Yes, Hemant. What are you doing here?
So, one minute, sir.
Hello.
Sir, doing, sir.
Fine, fine. Just one more minute.
So, root 3 A by Q now, sir.
Root 3. Yes, what is that? Root 3?
Sir, root 3 Q A now, sir.
Root 3 Q by A. Root 3, you are saying the value of capital Q is root 3 Q by, yes, root 3 Q by
Sir, root 3 A by Q, sorry, sir. Root
root
3
3
A
A
by
by
Q, sorry, sir.
root 3 A by Q. Is
Yes, sir.
this? No, it's wrong. See where you have gone wrong. Where you have gone wrong and how. See one thing. mm, that the distances between all these three charges is same. Okay, all these three charges are kept at same positions. Okay, distance is a by 2. Distance is given as a by 2. How much charge should you keep at the center so that the system remain in equilibrium? So first of all, you should understand that this charge, a small q charge, is being pushed by these two charges in this direction and this direction respectively. Is it not? Yes, because they both are positive. This is positive, that is also positive here. It means to pull it back, there should be a negative charge. So there should be a negative charge first of all. So there you have gone wrong. You did not say negative. Next is equilibrium means net forces are zero. Means whatever force these two charges are applying on this small q, that force must be encountered by the charge at the center. Okay. And can you tell me what is the distance? This is a by 2. This is 30 degree. So what is this hypotenuse? This hypotenuse will be what? Yes. Can you tell me what is this hypotenuse?
So we can take also cos 30 equals to
Cos 30
a
equals
by 2
to
by hypotenuse.
adjacent upon hypotenuse. So hypotenuse will be equal to a by 2 upon
Root 3 by 2.
cos 30. Cos 30 is root 3 by 2. So
A by 2.
by 2 cancel. We will get a by root 3. We will get here what?
A by root.
We will get here hypotenuse as a by root 3. A by root 3. Now, here the force is what? In this direction, the force is K Q1 Q2 upon R square. Similarly, here also it will be K Q1 Q2 upon R square. Okay. So the resultant will be what? Again, this angle is 30 degree. This is force F. If this is F, then it will be F cos 30 plus F cos 30. 2F cos 30. This will be 2F cos 30. So what is 2F cos 30? 2 into K Q square by A square F cos 30. What is cos 30? Cos 30 is root 3 by 2. This 2 and 2 cancel. Ultimately, the force we are getting is K Q square by A square into root 3. This should be equal to the inner force. Means K Q square upon A square into root 3 is should be equal to force between these two charges. K Q1 Q2 upon R square means A square by 3. 3 will come here. Okay. Now, again this K and K will cancel out. A square and A square will cancel out. Q square and this Q will cancel out. This 3 will go down, will come here. This root 3 will cancel it out. So capital Q will be what? Yes, what will be the capital Q? Hello, can you tell me?
Sir, it's cube root. Sir,
Why
it's
cube?
cube by
It is not cube. It is not cube, it is 3 only. It was A square by 3. This 3 went there. It is not cube.
sir,
So
it
this
is
3
like
went there, it became root 3
3 by
here.
A.
A is cancelled out. Where are you getting A? Did you see what we did here? Have you seen it?
Yes, yes, I
I
have
think
seen.
not. See this? Again, let me do this. Don't get confused. Don't get confused. Please pay attention. So force will be K Q square upon A square into root 3. Okay. This force plus the force which is this one, they must be 0. This force is K Q1 Q2 upon R square means A by root 3 whole square. Take it on that side. We can write K Q upon A square by 3. This 3 will come here. It will become 3 like this. Next is K. It will go there on that side of equality. K Q square root 3 upon A square. A square cancelled out. K cancelled out. Q power cancelled out. So what it became? A small q is equals to minus 3 minus root 3q upon 3.
By
This 3
3.
will go down there. This 3 will cut here and answer is q is equals to minus q by root 3. This is the answer written here, minus q by root 3.
Yes, sir.
Okay.
Yes.
Got it now?
So copy it, sir.
Copied?
So copy it, sir.
Fine. Please note it down carefully, okay?
Yes, sir, I noted.
Fine. Next question. Question is, where should we keep a third charge on a line joining two charges such that third charge is in equilibrium? Such that third charge is in equilibrium. Solve it out. Yes, done.
Sir, we get R and R by 3.
Hmm? What is the answer?
So, R and R. Sir, R by 3 and 2
R
R
by 3.
and 2 R by 3, sir.
See, first of all, again, at equilibrium position, net force must be zero. So we will assume a point in between. Let us say that distance is x. The remaining distance will be L minus x, is it not? Yes. For equilibrium, the two forces must cancel each other. The force of 4q must cancel the force of q. Both are positive, both will be opposing in nature. So both of these two forces are equated with each other. K q1 q2 upon r square. So K q 4q upon L minus x square. K small q upon x square. Getting it? Everything else will cancel out. What I am getting here? L minus x whole square equals to 4 upon L minus x whole square equals to 1 by x square. This I am getting. From here we are getting L minus x upon x is plus minus 2. Okay, it is plus minus 2. It means what? It means either L minus x is plus 2x or L minus x is minus 2x. So negative value of x is not possible. So x is L by 3. Very good. X is what? X is L by 3. So at this distance, whatever charge we are going to keep, that charge will not leave its position. Got it?
Sir, got it, sir. Yes.
Fine. Now, next, let us come upon equilibrium of the suspended point charge system. What is happening here? Two point charges are there, and these two charges were hanging through a wall as shown. Yes, these two charges were hanging through the wall as shown. A single roof. They were hanging through a single roof. Now what happened? Because of the electrostatic repulsion, both of them have same charges q. Now because of the electrostatic repulsion, they both will have some gap with each other. What will be that gap? Yes, what will be that gap? We don't know about it. So let us assume that the distance between the charges is small x. And for the equilibrium condition, the total force, all forces must be balanced. So first of all, we will draw the free body diagram of the charge, and then we will proceed. So in free body diagram, we saw that tension is having two components. What are the two components of tension? Tension is having two components, T cos theta and T sin theta. Now these two components of tension, these two components of tension, they will be balanced by electrostatic force and gravitational force of the charge. The charge has a mass small m. It is given in the diagram. Okay. Got it now? Getting something? Any doubt?
Sir, no doubt, sir, got it.
Fine. So just form the equation then. T cos theta will be equated with mg and electrostatic force will be equated with T sin theta. Okay. Now what to do? Just divide these equations by one another. This is equation 2 and this is equation 1. Divide both of them. T and T will cancel out. We will get tan theta equals to this kq square upon x square mg. Now if theta is very very small, then we can replace theta with and theta is equals to arc upon radius. Now what is arc? This is the arc, and that is L is the radius. Not that this is the full arc and L is the radius. So we write what? Arc upon radius. Arc is x by 2. Radius is L. Arc is x by 2. Radius is L. So theta is coming out to be arc upon radius, which we wrote x by 2L. Therefore, tan theta, we took out the tan theta, and by equating, we got the value of this equilibrium position x. Got it now? See, this formula is not to be memorized. If you can memorize it, then better. But the procedure is very, very important. In all the questions, we will be applying procedure only. Okay,
Yes, sir.
fine. Take it down.
So copy it, sir.
Copy.
So copy it, sir.
Fine. Now again, let us take another question. Write down the question. Three equal charges of charge plus q are moving along a circle of radius r and a point charge minus 2q is also placed at the center of the circle. If charges are moving with a speed if charges are moving with with a constant speed, write down with a constant speed, in the circle, then calculate the speed of charges. Given that this is a circular path, and on this circular path, three charges are there. This is in this direction. Yes, solve it now. Question is visible. This is the center. This is the radius r, and it is moving with a velocity v. At this center, another charge minus 2q is present. Solve it now. Try solving it. Hello, am I audible?
Sir, doing sense.
Fine, fine. Solve it now.
Sir, not getting sense.
See, read it twice. What is happening? First of all, try to understand that what is happening here. Hello. Yes. Are you getting the question? Tell me what did you understand from this question? Yes,
So,
Hemant.
so that's three equal sellers are moving on a circle.
Yes, they are moving on a circle. Now, first of all, tell me, whenever anything moves in a circle, what kind of forces are needed? Do you remember class 11? Zero
Centrifugal,
force,
centripetals.
centrifugal and centripetal forces are needed. So here also there must be one centrifugal force. Centrifugal force will appear in the outward direction, and to balance that centrifugal force, there must be an inward force. What should be that inward force? Can you tell me? Electrostatic force here is the inward force. So here electrostatic force will act as centripetal force, and centrifugal force mv square by r will be balanced by that centripetal force. Getting it? Now remember one thing, other than centrifugal force there is one other force which is in outward direction. See, only this force is attractive towards the center. These two charges, these other two charges, what will happen with these two charges? These two charges will repel. They will repel in this direction. Plus mv square by r. So this is electrostatic repulsion and this is mv square by r centrifugal force. These three should be balanced by this force. Okay. Now I gave you the hint to solve it. Now you must solve it. Okay. Getting it?
So getting serious.
Fine. So solve it and tell me the answer tomorrow. Question is taken down?
It's a question copied sellers.
Fine. Take down the question and this diagram as well. Our next class will be at 7:30 today. Okay?
Yes, sir, okay, sir.
Okay, thank you.
So thank you, sellers.
అమ్మా అమ్మా